In this last part of Lecture 4, I wanted to talk a little bit about the topics of power and how potential energy is related to force. So, in our problems of energy, we found that we can do work to put energy into a system, and this work can turn into an energy of motion, or it can turn into a potential energy of some kind. But we didn't talk about how quickly we can put energy into a system or how quickly we can take energy out of a system. And that's really what power is all about. Later on in this lecture, we're going to talk a little bit about how force and potential energy are related to each other. We calculated potential energy by looking at how force is applied over a distance. In fact, that work, the potential energy that could be put into a system, is related to the integral of force over some distance. So if we knew something about the potential energy and how potential energy changed as a function of position, could we find information about force as well? And it turns out that we can. But before we get there, I wanted to talk a little bit about the topic of power. So let's first go here to OneNote. And if we're talking about power, power is the change of the energy of a system with respect to time. So power really is d work dt or du dt if you're using U for potential energy. And so it's going to have units of joules per second. When we're taking derivatives like this, the ds or dt in this case on the bottom really does have units of time. So it really is a change in energy per change in time. And so this is going to have units of joules per second. Joules per second has a special name in SI as well. This is something that's called the watt. And the watt is a unit of energy, W. This is not the work. Now, here in America, when we think about power, we often think about the unit of horsepower. A lot of our vehicles come with a unit of horsepower attached to them. But the SI unit of power is the watt. And there's an equivalent between horsepower and watt that you see here. A horsepower is just a little bit short of a kilowatt, about 3/4 of a kilowatt. But if you're thinking about horsepowers in terms of kilowatts, you're going to be surprisingly close. Another place where we see this watt or kilowatt unit is if we're buying power from FPL, where we're buying basically units of kilowatt hours. So if a kilowatt or a watt has units of energy per time, but if we integrate over some time, this becomes an energy again. So in the case of a kilowatt hour that we may buy from FPL, a kilowatt being 1,000 watts, an hour being 3,600 seconds, a kilowatt hour is about 3.6 megajoules. What you're buying from FPL, even though that word watt is in there, you're not buying power from FPL. You're buying energy from FPL. That's what you're really buying. And there is an example that we have in the notes of me trying to figure out how much FPL would charge me to put a Dreamliner on top of one of the buildings here on campus. And it's really not much. Actually, since I made that example, the prices for FPL have gone up by almost a factor of 3. So now instead of being 50 cents, it would charge me about $1.50. Okay, fine, whatever. But what I'd like to do here instead is I also wanted to look at a special case of this power being the change in energy or the change in work or whatever you want to say as a function of time. So let's say instead of talking about power being the change in energy with respect to time, this is really the other side of the coin of energy being the integral of power over some time. And if we wanted to, so here, this is what we're doing is work. We're putting work in right here. And the amount of work that we're doing is we're integrating the power over some time. And this power can have any sort of a function. The power can change as a function of time, initially being small, later being large, initially large, later being small. It can have any sort of functional form as a function of time. And by doing this integral, that's how we find out how much energy we put into the system. That's what work is, putting energy into the system. Now, once the energy is in the system, it can take a variety of different forms, of course. It can be kinetic energy. It can be potential energy of a variety of different forms, right? So I wanted to look at some example. What if we wanted to have a Honda Accord, and we wanted it to go from 0 to 60, and we wanted to find out how fast it could do it? How fast can a Honda Accord, I guess this is a new one, I just looked up numbers on the internet. And here's his miles per hour. Now, that being said, this is, I guess I got it off the internet, so this is probably a 2022 Honda Accord, most likely. I don't know what the option packages are or anything like that. But what I found on the internet is that the weight, let me write it a little bit differently, of this Honda Accord is 3,362 pounds. Okay. We would like the Honda Accord to get up to a speed of 60 miles per hour. And I know that the Accord has an engine that can deliver 252 horsepower. Now, this power is not going to be constant as a function of time, but we could approximate constant. So we'll approximate that this is a constant power, even though it really is not. But we'd like to find out the time it takes for the Honda Accord to get from 0 to 60 miles per hour. So looking at this relation here, we're going to not store any potential energy in gravitational terms. We're not going to store any potential energy in compressed springs or things like that. We're going to change the kinetic energy of the Accord. So when we are doing work, we're going to find out that 1/2 mv squared worth of energy is related to the integral of power over some time. And if we're assuming a constant power over that time, this is a perfectly valid relationship. So if we want to find the time it takes for the Accord to do this, we have to solve for time. And so for us, the time is going to be mv squared over 2 times the power. Now this is functionally what's going on, but up here we don't have any of our SI units that we need. So let's convert this weight to a mass, and this is 1,525 kilograms for mass. Now this is a weight, this is a mass. Okay, so to take this mass multiplied by g, then you'd get newtons. Newtons converts to pounds. But there's converters on the internet. That's all I did here. Now, 60 miles per hour is going to be in the vicinity of 30 meters per second. But if we did an actual conversion, the velocity is going to be 26.8 meters per second. And this power, 252 horsepower, is going to be in the vicinity of 200 kilowatts. It's actually 185 kilowatts. So now we can use these units and plug in down here to find out the time. Let's pull up our calculator. I'm going to do the 2 times the power first and then put it in the denominator. So 2 times 185 times 10 to the 3 is this. Let's put that in the denominator. Multiply by the mass, which is 1525, and multiply by the velocity squared. So times 26.8 squared. I see 2.96 seconds. Now that's probably not exactly right. This is in the vicinity of correct, what a modern car can do, something in the vicinity of 3 to 4 seconds. Now the difference here is initially there is some sort of a power curve. You don't get the maximum horsepower of a gas engine initially. It works its way up to it as it spins up. So the power is actually functionally different than being constant. It takes a little bit of time, and so we're not putting energy into the system as fast as we think initially. But certainly this is in the vicinity of advertised times from 0 to 60. You get the quarter mile, that's over a distance instead of over a time. But you kind of get the functional form of what's going on, and this is how we can apply it. Power is the time derivative of energy. Energy is the integral of the power. Okay? So this is the first topic I wanted to talk about. And there's a few examples and forms and stuff that we could do with this if we wanted to. But what I wanted to do instead was also talk about not just the linkage and connection between energy and power, but I wanted to talk a little bit about the linkage and connection between energy and force as well, because that's also a really interesting topic. So let's go back here to OneNote. And that's related to here. So there are some certain forces that are related to potential energies. Gravitational force, spring force. Those are the ones that we talked about here. And there are certain forces that are not related to potential energy. Frictional force. Now, what's the difference between these two? So maybe I could have a ball and I have it on a table, and I can move the ball from one part of the table to another part of the table. And if I let go, it's not going to go back necessarily to where it started. Or if I was to take my coffee cup on the book that I commonly use and take the coffee cup, actually I've probably got the coffee cup here, and I've got the book here. Why not pull it up? So I see, for example, I've got my coffee cup on the book here. I can apply force over a distance, and I started at rest, I'm ending at rest. I did work. You saw me apply force. I applied it over a distance, but it's not like I'm getting that energy back, right? I mean, the cup slid, but now all of a sudden it doesn't have any kinetic energy. It must not have any real potential energy, I think, because it's just sort of sitting there. When I let go, it didn't do anything. Okay, now we could look at a different scenario, which is not my coffee cup that could break, but I could look at the case of a ball. I could certainly once again apply force over a distance to lift the ball. And if I let go, the ball falls. This is a different scenario. It didn't just sit there and hang in the air. I put energy into the ball. I got that energy back. It took potential energy and turned it into energy of motion. These are two different scenarios. In one scenario, I did work and I didn't get that energy back. It turned into maybe energy of heat. Maybe it turned into energy of sound. It could have turned into all sorts of different things, but I certainly didn't get it back in the form of mechanical energy. But sometimes I can do work and I can get that energy back in the form of mechanical energy. These are two different kinds of forces. And so the first one I'm talking about, related to potential energies, are forms of work that I can do and get that energy back. There are other forms of work that I can do, such as against frictional forces, where I don't get that energy back. So there is certainly a relationship between force and potential energy in some situations. And in some situations, there is not a relationship between force and potential energy. Every time I do work over some distance, I am putting energy into the system. But not all energies necessarily go into a mechanical form. And that's really the difference between two different kinds of systems. One of these is called a conservative system, and one of these is a non-conservative system. In a conservative system, the work done in moving an object between 2 points is independent of path. And also, work around a closed path is equal to 0. So let's look at the case of the ball. If I was to lift the ball and then move it over to the side, I have moved the ball between 2 points. What if I had instead just gone in a straight line? Would its potential energy be any different than it was before? Maybe the amount of force that was applied by me is slightly different, but it still has the same potential energy it had before. It's at a certain height with respect to its initial height. So whether I went along the straight line path or I went up and to the side, we get the exact same phenomena. This is a conservative system. But the case of my coffee cup, where I pushed the coffee cup to the side and then it sat there, it turns out that I could lose lots of energy in frictional situations. What if I had done a weird circuitous spot to move the cup to the new position? Well, then I would have been applying force over a larger distance. And still, none of that energy is conserved. So this is a way of getting a cup from one position to another, and depending upon the path, different things can happen. Different amounts of work are required. And if I took that cup and then moved it back to where it started, I certainly applied force over a distance. It didn't get back to that starting position for free. I had to do something to get that back. I had to do more work to do that. So this is the equivalent of a non-conservative system. So if you're talking about potential energies, you have to be talking about conservative forces. That's the only thing that you can have. Non-conservative forces like friction cannot be described with potentials or potential energy. Only conservative ones can be. Now, that being said, there is a relationship between potential and force. And if you're following along with the OneNote pages and the like, this is where I'm sort of sitting here. But let's say what we wanted to find is how we are storing objects, energy in some system, and how we can use that energy to then apply forces at a later time. So, as you might see here, to do work, I'm integrating force over a distance. I'm going to go to a piece of paper here, and we're going to do this a little bit in real time. I know that if I want to do work, what I'm doing is integrating force over some distance. That's how I get work. Now, maybe we're looking at the case of a spring or something like that. The force that's applied by a spring. So maybe we're pulling some object to the right, but the spring is trying to bring it back to equilibrium. As we pull to the right, the spring pulls to the left, right? Left, correct. I should write it that way. So let's look at the case of a spring. There, our force is going to be minus kx, where k is the spring constant. We're integrating dx. But we're integrating from maybe some initial position to some final position. Now, doing this integral, the minus comes out, the k comes out. We're integrating x dx, which is 1/2 x squared. But we still have to apply this with the limits of integration. And so what we find is that we get 1/2 k x initial squared minus 1/2 k x final squared. This is an initial potential energy. This is a final potential energy. And the order is not the order that's needed for change in potential energy. Change in potential energy is U final minus U initial. So this is the negative of the change in potential energy. Or to look at this, if I want the spring to do positive work, I have to lose potential energy. So they must lose potential energy. If I want the spring to do work, it must lose potential energy. And so we find that there's relationship here for not only what the work is being done, but potential energy as well. So whether we're talking about me doing work or the spring doing work, there's a lot of ambiguity in what that work is going to be. But the potential energy stored in some spring, that's really pretty clear. I mean, so as we're doing work, the spring is doing negative work. That's how the potential energy system goes about. But if we're looking at energy stored in some spring, we now get a connection between potential energy and force, as opposed to work and force. And what we see here is that if change in potential energy is negative the integral of force over position, mathematically, that's the same thing as saying that force is minus the change in potential energy with respect to position. These are two sides of the same coin. I can either integrate force over distance to get potential energy, or I can take the derivative of potential energy with respect to position to get force. Interesting. Now, this energy is a scalar. Force is a vector. And so what we're really calculating with this derivative of potential energy with respect to x is an x component of force. We could also get a y component of force by looking at how this scalar quantity changes as a function of y. We can get a z component of force by figuring out how the potential energy changes as a function of z. And so we get this vector property force by taking the negative change in potential energy with respect to x in the x direction, change in potential energy with respect to y in the y direction, change in potential energy with respect to z in the z direction. And so this quantity, change with respect to x in the x, change with respect to y in the y, change with respect to z in the z, these really should be partial derivatives. You'll talk more about the difference between partial derivatives and total derivatives in Calc 3. But this gets a special name with the del operator. This is a derivative that gives directions, a derivative of a scalar that gives different directions. And so in the book, he has this relationship. Here, this is a scalar quantity u, this is a vector quantity f. If I can take the derivatives of this scalar quantity with respect to those different directions, so to speak, different coordinates, you can find out what the components of force are going to be. Now, most often in this class, we're just working with this x component here. We're doing this. We might have a potential that depends on position x, and we would like to find different kinds of forces. But force is derivatives. It's like slopes. So if I knew what energy as a function of position was, force is going to be related to the slopes of that function. But it's going to have a negative sign. So what I have in the notes to kind of look at this is going down here to the bottom. What if I had a weird peak function like this? On the right-hand side, the derivative of energy with respect to x is a negative slope, which means that we have a positive force or a positive x component of force. Things are going to get pushed to the right if put on the side of this hill. Similarly, here on the left, you see that the derivative of energy as a function of position is a positive slope. So adding that negative sign means that force is going to be to the left. If I was to put a ball on the left side of this hill, it's going to get pushed to the left. Things on the right get pushed to the right. Things on the left get pushed to the left. Oh, okay. So you're telling me that the way something is going to be pushed could be determined by just looking at this energetic landscape. Sure. And in a way, this picture is very much like what we're doing with gravitational potential energy. Balls will roll from the top of the hill to the bottom of the hill. And maybe that hill is over here on the left, and maybe that hill is over here on the right. But balls will roll down the hill. If we could just balance a ball at the very top, then it would sit there, but that is an unstable equilibrium. Any little tweak one way or the other, and the ball will roll down the hill, right? That's what this is talking about. If we were to have some conservative system where our work can be stored in potential energy, then forces on anything that is in that energetic landscape are going to lower the potential energy of the system. So yeah, I could do work to put a ball to the top of a hill. But if I was to let go, the ball is going to feel a force that draws it down to the bottom of the hill again. That's what this is saying. Forces are going to lower the potential energy of some system. That's how it works. And so let's just look at one quick example of how we can apply this. So let's say I had some potential energy. And we're going to look at this here on paper first, and then we'll go to Mathematica and see what it kind of looks like and give ourselves confidence and faith that it's working the way it's supposed to. But I'm going to say that this is alpha x minus beta x squared. And for later, if we need it, alpha is going to be 3 joules per meter, which is actually a Newton. And beta is going to be 2 joules per meter squared. So these are just numbers. We can put this in here. Now maybe first I want to find out what the force is. What is the force as a function of position? And so to calculate force, and this is just going to be an x component of force because we only have x's, we're going to be looking at the change in potential energy as a function of x. And here I've got an alpha x, the derivative of this is just alpha. Beta x squared will be 2 beta x. And so if I factor that minus sign through, this is 2 beta x minus alpha. And this is what the force in the x direction is going to be. Now there's a couple of other things that we can find out after this. There is probably some position where the force is equal to 0. Can we find a position where force is equal to 0? Now, where force is equal to 0 is either going to be the top of the hill or the bottom of the hill, where energy is a maximum or where energy is a minimum. And so we can find force equal to 0 by taking this thing here, 2 beta x minus alpha, and setting it equal to 0. So from this, 2 beta x is equal to alpha, x is equal to alpha over 2 beta. At this position, our force will be equal to 0. And if we wanted to plug in some numbers, alpha is 3, 2 beta is 4, this is 3/4. And units, joules per meter divided by joule per meter squared is a meter. So it says at x equals 0.75 meters, we are going to have force equal to 0. This is either going to be the top or the bottom of our energy landscape, but this is going to be one of those inflection points. Now, what are some other things that we could look at? What is the force and direction at a certain value of x? And direction at, say, x equals 2 meters. Well, now, once again, we know this expression for force, so we could just say force at x equals 2 meters is going to be 2 beta 2 meters minus alpha. Now, okay, so we can put this in here, and we know a lot of these things. This is 2, beta is 2 times 2, this is 8, alpha is 3 minus 5. So this is going to be 8 minus 5, 8 minus, 3. Now, what are the units of this? Beta is joules per meter squared times meter, so this is a joules per meter. Alpha is a joule per meter. Joule is a force times a distance. Force times distance divided by distance, this is a force. This is 5 newtons. So it really does have the correct units. Now, this is a positive number. This is not a negative number. Because this is positive, this is a force in the positive x direction. Looking at a plot of this means that this would be a force to the right at this position. So when we're at x equals 2 meters, we're getting a force to the right of a certain value. Now, maybe another thing we want to look at. So what is the value of potential at this position? So here we have our expression for potential, which is alpha x minus beta x squared, but we have a certain value of x, right? Alpha times this value of x is alpha over 2 beta minus beta, we have to do x squared, so alpha over 2 beta quantity squared, which is alpha squared over 2 beta minus beta alpha squared over 4 beta squared. Beta cancels with beta here. We've got an alpha squared over beta. Here we've got a 1/2. Here I've got a 1/4. 1/2 minus 1/4 is 1/4. So this is alpha squared over 4 beta. This is the value of the potential where the force is equal to 0. Now we can look at numbers here. Alpha squared is 9, 4 beta is 8, so this is 9 1/8. Or 1 1/8, so this is 1.125. What are the units here? Alpha squared is joule squared per meter squared divided by joule per meter squared. The meter squareds cancel out, but joule squared divided by joules is joules. So it really does have units of energy just like it's supposed to. Now I don't know whether this is big or small, right? So, but we can do some calculations that relate force and energy. We can find out where does force go to 0? We can find out what values of force are at certain positions. We can find out at certain positions what the energy is going to be. And maybe we wanted to spend a little bit of time looking in Mathematica of how this might look. So let's go to Mathematica here quick. You see Mathematica? I don't yet. Maybe I wanted to look at a plot of this thing. So let's plot. This is going to be alpha x, which is 3x minus beta, which is 2x squared. And I want to plot this over some range of values. X being, I don't know, -3 to 3. See what it looks like. And lo and behold, we see this sort of peaked functionality here, right? Where is the top of the peak? Somewhere about here. If I was to actually find the top of the peak, we could, but certainly our initial calculation of 0.75 meters, that looks pretty realistic. Similarly, if we were wanting to find out what the force is at a certain value of x, we went over here to 0.2, and we found out that we had a force to the right. We're on the right-hand side of this hill. If we were to put a ball here, of course it would roll down the hill. It would feel a force to the right. So seeing that makes a lot of sense. What is the maximum value of our energy? We didn't know if it was maximum or minimum, but at this certain value, okay, that's -1, -2, -3, -4, -5. This is +1, almost +2. And it was supposed to be 1.125. Yeah. So we're getting things that make sense from what we were calculating before. So let's say we wanted to find where the value of x was equal to 0. Or where the force was equal to 0. So we could take this thing, copy. Let's take the derivative. We're going to take the negative derivative of this with respect to x. And that's this. We're going to take this and set it equal to 0. We're going to solve this equals 0 for value of x. And yeah, x is equal to 3/4, just like we found before. I took that. That's where the maximum value is. If we were to take this x 3/4 and plug it into here, only this is going to be 0.75, and this is 0.75. Boom. The exact same thing that we got before. So that's where the top was. If we wanted to find out slope as a function of position, we could do that too. So what we were doing here is we actually found out what the force as a function of position was. Let's plot that. I'm going to take this thing here. This was the force. It included the minus sign and everything. So let's see what it looks like over the same range, -3 to 3. Huh. Well, yeah, this is linear. It has a slope of 4, intercept of -3. That's exactly what we see. This is linear behavior. And now comparing this curve up here, which is energy, and we're just do a little bit of dressing up here to make it look pretty. Let's call this x in meters, and this is u in joules. Okay, so this is our energies, and as we might expect, anything to the right of 0.75 is going to make the ball go to the right. Anything to the left of it is going to make it go to the left. Forces to the right are positive on this side. Forces on this side are to the left, or negative. So now we go down here. Sorry. Forge. Let's do this here. So again, this is X in meters. This is force in newtons. And so what we see is any force to the right of 0.75 is a positive force. Any force to the left of 0.75 is negative. So if I was to place an object over here at point 2, it's going to feel a force to the right. If I put it at -2, it would feel a force to the left, because we're on the different sides of the hill. Not only that, because we're looking at force as a function of position. If I go to position 2 and I go here, yeah, the force is positive 5 newtons. It's to the right with a certain value from here. So this force is the derivative of this thing. This is an energy landscape. Energy is a function of position, has all of its variety of forms, but it's just a scalar, only a scalar. By taking a directional derivative, essentially, we can find out how these directional forces are related to that energy. And similarly, if we were to move an object here along this force as a function of position landscape, we're determining how much energy is going into the system. By compressing the spring or elongating the spring or lifting the object, we're putting energy, potential energy, into that system in a variety of different ways. So this is the last thing that I really wanted to talk about for this little lecture. There really is a connection between how quickly or slowly we can put energy into or take energy out of a system. That's what power is all about. It's telling us how quickly we can do these things. But there really is this deep relationship, a connection between force and potential energy. And whether we're integrating or taking derivatives, it's the same side of the same coins. This is the relationship between these two things.